Alright guys, welcome back. Today we're going to talk about the Central Limit Theorem again, and we're going to apply it to means. Uh, so I did a little bit of research on trying to find a question I wanted to kind of make up. We just do it as we go. Buddy of mine is a farmer, and he just bought this breed of cow. He actually bought two of them. They're about a year old, and he started talking about the weights of them. So I did a little bit of research. Wikipedia is not a very good search engine. I just had it up there for whatever reason. But kind of just going off the ranges that I've read off different sites, I want to kind of give you this information here, and we'll start off our question. The central limit theorem, no matter what population your random sample comes from, it's kind of like just getting started here. Again, no matter what the population or what population your sample comes from, the shape of the sampling distribution is going to be close to normal, as long as it is a large sample size, which makes sense. If you only sample, like, in this case, 3 cows, I mean, they could be really, really, really spread out or really biased. But the larger the sample size used, the more accurate the normal approximates the sampling distribution for the mean. And that's what we're going to do. We're going to use the central limit theorem to kind of make a prediction about the mean weights seen in random samples of 100 mature Maine Azure cows. I can't speak French, so you'll have to deal with that. But yeah, so look, given this information here, okay, we're going to go with that as our population mean. And then our standard deviation obviously is going to be 210. All right. So we'll keep that in mind here once we start calculating. Again, here's our question. Our sample size, N, is 100. I did that for a reason. Okay. 100 is a perfect square. So I'm going to roll with that number. So we want to predict what the central limit theory would say about the mean weight seen in random samples of 100 mature Maine Azure cows. So let's take a look at this. 68%, 95%, 99%. Remember, if you're 68% of your data is one standard deviation within the mean, or within one standard deviation of the mean. 95% would be 2 standard deviations within the mean, within 2 standard deviations. And 99.7% of our data is going to be within 3 standard deviations of the mean. So we're going to kind of follow this as a formula and calculate. First of all, let's take care of this little guy right here. So let's take a standard deviation divided by square root of n. Let's go ahead and calculate that number. Remember, our standard deviation was, I forgot, embarrassing, 210. Okay. Divided by square root of 100. I know that's my sample size. So you got 210 divided by 10. So I end up with 21. All right. So I'll write mu down here just so that I have it. Mu was 1740. Okay. Now what I'm going to do is go to the graphing calculator here and start punching in my numbers. I kind of feel like an idiot though about this part because One of my kids at school was like, "Mr. Seidel, why are you punching everything in so much? Why are you punching it twice?" I'm like, "What are you talking about?" We started punching this in. Let's just use this for example. We got 1740 plus 1 times 21. I'm just going to write 21. I like to close parentheses. I'd hit enter. Okay. So our boundary, I'm going to write it right here in a minute. Or write it and let you see it here in just a sec. So we'll have this, and I'm going to write that 1761 right here. When you plus, it's kind of going to be the upper bound of things. I started punching this all in again, and they're like, "Mr. Saw, just hit second, enter, and change the plus to a minus." I'm like, okay, that's pretty genius there, as long as you're just punching it in one time. So I'm going to hit enter again. I get 17, 19. So 68% of my data is going to be between 1,719 pounds and 1,761 pounds as far as our mean. Now let's punch in the 95%. Now notice we got 2 times this, so we're going to have 2 times 21. I'll bring up the calculator again. I'll just keep it all right there. Let's just go ahead and hit second enter again. And you should be able to just hit second, delete, which is an insert button. And let's just put 2. Change that to a plus and calculate that. So we're already calculating the 95%. That's an ugly looking Y. So I'll write that number down, 1782, 1,782 pounds. I'm barely fitting there. So now I can just hit second, enter again. Just go through all the motions here. We're going to find this thing gets quirky. So bear with me. Change it to minus 1,698. So now, as our percents get larger, we're trying to find 95% of our data. Our ranges get bigger. We got more room to kind of make a prediction. So far in a 68% of random samples of 100 mature cows, the mean weight will be between 1,719 and 1,761. And in 95% of such samples, now we got a 1,698 between that and 1,782. Okay, now we're going to find the 99% of such samples. What could the mean weight be between? All right, so let's go back to our graphing calculator. We'll just hit second, enter, and we got to change a couple things. Let's hit delete there, make that a 3, make a plus sign here. Now I'm getting a little crazy. Forgot to hit insert. So now I have that. I'll hit enter. Now I got 1,803 pounds. So the mean weight could be between something and 1,803. Let's find the last piece of the puzzle. Change it to minus. Bingo. What's his name? Oh, now we got 16. 77 as 99.7% of such of our samples that we have, the mean could be between this range right here. Okay. One thing about central limit theorem, the central limit theorem says that all we need to model the sampling distribution is a random sample of quantitative data and the true population standard deviation. But that could be a problem. How are we supposed to know the population standard deviation? We may not know it. We weren't given that in the problem. So what would we really use? We would just use our sample standard deviation. That'd be the sensible thing to do. So pretty much this concludes today's video on central limit theorem again and dealing with the means. Hopefully this helps. And until next time, rock steady or don't rock at all.